Hola. In this presentation, I will highlight some of the key findings from my PhD research, which contributed to the understanding of the evolution of the Santos Basin offshore Brazil. The stratigraphic architecture in salt basins is controlled by the solubility of the different evaporite minerals and basin configuration. Gypsum is mainly deposited as marginal wedges, and if a major sea level drawdown occurs, Hela will be precipitated in the central deepest parts of the basin. In very extreme conditions, bitter salts as carnallite may form. Gypsum will be again precipitated in the basin as refloating occurs. This defines a complete evaporite cycle of filling and desiccation of the basin. In plan view, this will look as a bull's-eye pattern for an enclosed basin and as a teardrop pattern for a restricted basin. In passive margin, tilting basinwards and differential sedimentary loading on the soil would lead to gravity gliding and gravity spreading, and that is expressed in a thin skin extensional domain, a translational domain, and an area of contraction, characterized by a variety of structural styles along the slope that will impact the seafloor and the distribution and architecture of the water-clastic systems. Salt dissolution may also occur, leading to the formation of cap rock and dissolution breccias. The data available for the study included a 3D time-grid seismic volume, a 2D depth image seismic profile, and 8 public wells shown in yellow. The salt-dominated Ariri Formation was deposited in the late Aptian. During my PhD, I tried to characterize the thickness variability and the stratigraphic architecture within the salt to provide some clues about the depositional basin physiography and hydrology. And this is one of the questions we address in this paper published at Geosphere. A major siliciclastic progradation was emplaced in the late Cretaceous, and previous studies suggest that most of the sediments were trapped behind a salt-controlled epicenter, the Albion Gap. In this paper, soon to be published in the APG Bulletin and available as a preprint, we demonstrate that sedimentation reached further into the basin. Here, I will try to answer and illustrate how salt tectonics control the water sedimentation in the Santos Basin. In the Paleocene, a non-sharp uplift led to a change in sediment supply, now focusing to the north and the Campos Basin. In this paper, we demonstrate there was also widespread salt dissolution expressed as salt karst in the Santos Basin. Here, I will illustrate how is that this dissolution occurred. Salt in the Santos Basin represents the southern part of a salt giant that was deposited during opening of the South Atlantic Ocean in extreme conditions that don't exist today in modern salt basins. An arid climate and a narrow seaway, similar in dimensions to the Red Sea, led to the position of thick salt in the basin center, thinning towards the basin margins. A volcanic seal located to the south prevented free seawater circulation to the north. That volcanic seal is represented by the São Paulo ridge and the Florianópolis fracture zone in this gravity map scaled to depth of pavement. These regional seismic lines illustrate salt thickness variations across the basin. The 3D seismic survey covers a large part of the São Paulo plateau and an intrabasinal high called the outer high, which includes also the Tupi subhigh and the Sugarloaf subhigh. This regional line illustrates present-day salt thickness variation across the Santos Basin. The study area covers parts of the mini-basin domain and the São Paulo plateau and fault belt in the contractional domain. In this area, the salt sequence is highly reflective and the base salt is dipping landwards due to the location of the outer high. This arbitrary line connecting some of the key wells and extracted from the interpretation of the 3D survey highlights intervals interpreted pre-salt, salt, and some of the post-salt units. The map is a nice opaque between the depth-converted topsoil and the depth-converted base salt. Here, white is thin and red is thick. Note the difference between a relatively more deformed area to the north and an area to the west of relatively less salt flow. This area of thicker salt corresponds to a structurally lower area in the base salt vessel structure map. This map also highlights the presence of the Sugarloaf subhigh and the Tupi subhigh, where some of the wells are located. If we zoom in into this north-southeast trending part of the arbitrary line, here we can see some of the proximal thick mini-basins with discontinuous welding of the mini-basin floor and bounded by upright salt walls characterized by rounded and more rugose crests where the intrasalt intervals are truncated. Units within the mini-basin are bowl-shaped due to vertical mini-basin subsidence and wedge-shaped, indicating shifting of the epicenters. This section also shows a more triangular-shaped diapier located at the ramp on the outer high. Mini-basins on the high are relatively thinner and shallower, and no welding of the salt is observed. If we now moved on the part of the arbitrary line connecting two wells on the Sugarloaf subhigh and a well in a structurally lower area, on the Sugarloaf subhigh, salt walls are characterized by strikingly nearly flat crests where the intrasalt is less reflective or characterized by transparent seismic facies. Mini-basins also occur in the distal area with thin salt and salt core anticlines only occurring locally. The ramp and the structurally lower area is characterized by salt core faults and thrusts where there is a step along the base salt. I will now show you a correlation between the wells in the structurally lower location and across the Sugarloaf subhigh and the Tupi subhigh. Interpretation of the wells indicate that the intrasalt is characterized by interbedded halite and hydrites and bitter salt, mainly carnallite. And we interpreted 12 complete evaporite cycles, meaning that this basin was nearly desiccated and refilled at least 12 times during deposition of the salt or evaporites in the late action. This intrasalt heterogeneity is what causes the highly reflective nature of the salt, mainly acoustic impedance contrast resulting from density and seismic velocity variations of the different evaporite minerals. This well correlation, of course, illustrates the present-day stratigraphic architecture of the intrasalt, and considering the salt-related deformation that has occurred in the Santos Basin and the long distance between the wells, we tie the wells and the seismic and interpret seismic events representing individual evaporite layers and also use relative acoustic impedance to have a more accurate interpretation of the intrasalt. I will now animate from the lower intervals some of the evaporite layers interpreted. For the lower interval, thinner salt on the high and thicker salt on the most distal and structurally lower intervals, and some of the anhydride layers on the high are pinched out or are not present to the north. where beaten salt associated to a higher salinities are only locally represented on the 2P subhigh. For the middle intervals, thickness variations of the intrasoil are less evident, and the evaporite layers or anhydrites are more laterally extensive from the high towards the northern areas, as can be seen in this carnallite layer tied to the wells and covering most of the study area. Overall, we found thinner salt and higher proportions of anhydrite on the Sugarloaf subhigh, and thicker salt and higher proportions of carnallite on structurally lower areas and on the Topi subhigh to the north. Now I will illustrate some salt tectonics controls on deep water sedimentation in the Santos Basin. In this map, purple is thick and red is thin. The post-salt is up to 4.5 kilometers thick within the proximal minibasins and thinner to the south. In the next slides, I will show you two sections, detailed mapping and seismic attributes to highlight some of the key findings about the fillings of minibasins A to E, and then move to the south to illustrate salt-related controls along the fault belt. This map is the isochron or thickness of the orange unit displayed with the top salt map to highlight the geometry of the bounding salt walls at that level. Depocenters are highlighted in blue and purple, and these are located in more distal locations along minibasin A, in central locations in minibasin C, and in a more proximal updip location within minibasin B, suggesting frontal confinement of the sediments. Once this intra-minibasin depocenter was filled, sediments spilled along minibasin B towards distal locations, as highlighted in the isochron of the overlying yellow unit. This isochron highlights shifting of the depocenter in a more proximal location to a more distal location along minibasin B. An arbitrary line along the minibasin shows that frontal confinement was due to the presence of a salt roller within the minibasin. Seismic attributes highlight some of the deepwater clastic systems within the minibasins, and the positional dissection of channels and minibasins by the rising salt walls. To the south, in the inner fault belt, we identified submarine channel systems within the yellow unit that extend for more than 100 kilometers downslope. Salt core faults, anticlines, and salt walls locally controlled the architecture of the submarine channels and lobes. Channel 5, for example, flows downslope and encounters a north-south trending salt wall and bends parallel to the axis of the minibasin. Within this minibasin, the channel is thicker, and the isochron highlights that the channel is flanked by wing-shaped levees that thin and unlap the bounding salt core highs. The intra-levees reflections unlap and are rotated on the limbs of the salt core anticline, suggesting depositional movement. The architecture of the levee provides a stratigraphic record of the structural growth of the bounding salt core height. These clastic systems record the last evidence of the water sedimentation in the Santos Basin. The end of the water sedimentation was followed by widespread salt karst. In the next slides, I will illustrate evidence of salt dissolution at 3 locations, including truncation of the intrasalt, salt karst features, and the formation of the overburden, suggesting subterranean dissolution. Oval-shaped and circular depressions that we have interpreted as sinkholes are identified in highly rugose and rounded crests of salt walls. Here, the top salt overlies highly heterogeneous dipping and truncated intrasalt intervals. Mounted features along the top salt are identified atop halite-rich salt walls. We interpret these features as less soluble residuum, potentially pockets of anhydrite left after dissolution of the halite-rich intrasalt. Deformation or collapse of the units above dissolved salt crests is expressed as pseudo-downlapse, chaotic seismic phases where the top salt is lower, and vertical fissures or pipes. I illustrated how thickness and composition of the intrasalt vary laterally and are spatially related to structural domains. Thinner salt and higher proportions occurs towards the structurally high sugar loft compared to flanking structurally lower areas where salt is thicker and anhydrite proportions are less. We proposed that the lower intervals filled a pre-existing reef-related relief within which the sugar loft, so high, represented an intrabasin structural high with relatively shallower water compared to flanking areas. Subsequent deposition occurred in a basin with a more subdued relief and reduced accommodation. I illustrated some of the salt tectonics controls on intraslope deepwater sedimentation in the Santos Basin, including ponding in updip epicenters and dissection of the channels by rising salt walls. In the fault belt, we saw local changes in the architecture of the systems, like diversion and lateral confinement along minibasins. Based on the seismic expression of the crests of salt walls and the overburden, we suggest that widespread salt karst, some of which I have illustrated in this presentation, is due to superjacent salt dissolution by sodium chloride under saturated seawater that penetrated the very fine-grained unlithified overburden during exposure at the seafloor. Gracias.